Now, at the end of the 19th century, so the late 1800s, the car industry was undergoing an explosion because, of course, it was seen as, and in fact is, a very important market where fortunes could be made. So lots of little car companies were popping up all over the place to make cars, and they were trying to improve on what went before and make their cars better. Now, a lot of the time, it's thought that when you're designing something, you should design for the best. And if you happen to be working in research, well, that's very true. But if you're working in manufacturing, what you should design for is cost. And the reason's obvious. If you make something that'll do the job and it's cheap, the mass market is open to you. If you make something that's 1% more efficient but 10 times the cost, well, pretty much you're doomed. And that was the experience of lots of these little car companies, including a car company you've probably never heard of called the Lanchester Car Company. Now, the Lanchester Car Company was set up by three brothers, Frederick, George and Frank, and what they aimed at was solving the problems of the car. And they were extraordinarily innovative because Frederick was a very well-respected automotive engineer, and he brought his brain to the problem, and they came up with some astounding things. I mean, they were the first company to create disc brakes. They also used epicyclic gearing in their gearboxes. However, they went bankrupt only 5 years later in 1904. The receivers came in, reorganised them, they ended up being owned by Land Rover, which of course is now owned by Tata. And the big issue that they had was, it was just too expensive. Now, one of the issues that they looked at was the nature of the drive. I mean, if you think of a car now, it's 4 pistons in line, and of course they explode and lump through. The ride in a car back then was particularly rough, and the Lanchester brothers wanted to solve that problem, and they created something called the Rhombic Drive. In a rhombic drive, a rigid piston rod is connected to one side of a rhombus instead of a flexible rod connected to a crankshaft. And of course, as the piston moves, it deforms the rhombus. As the rhombus deforms, it's attached to 2 cranks, gears, flywheels that move in opposite directions. This distorts the other side of the rhombus, and so first it flattens out, returns to its shape, and then flattens on the other side, at bottom and top dead centre. Now, the benefit of the rhombus drive is it gives a very smooth movement from linear to rotational. The disadvantage is, well, it's more complex, there's more parts to manufacture, and the tolerances of having a double piston system like that are quite tight indeed, meaning you don't see it much in motor vehicles these days. But in a Stirling engine, of course, one of the pistons isn't actually a piston, it's a displacer. The whole job is just to take up space so that the air moves between the hot and the cold side, and tolerance isn't so much an issue. So you find rhombic drives in Stirling engines even today. So what I thought I'd do is create a rhombic drive. Now, one of the things about designing stuff is that you don't have to design everything from scratch all of the time. Now, here's the Tinkercad drawing I did for the hypercycloidal engine, and this is the flywheel. Now, it took a fair bit to do, and I really quite like it, so we can reuse it in the new model that we're going to make. To do that, just click on it and export it as an STL, and then we go back to the dashboard, open up a new workspace, and this time we can import it. And there it is. Now, there are a few changes I want to make to it because there are some things I don't like about it for this new design. For example, it's 45mm high, which I think is a bit too big, so I want to reduce it. So pull on a basic cylinder primitive that's a hole. The size of this is 150 by 150. I want it 30mm high, so type in 30 to move it 30 off the bed, and then on the size of it, type in a bit bigger than the size that you want to cut out. Center them to each other, and then if we merge those, we've got the flywheel size I want. Now, I designed this with a square peg in the center because I wanted to link to a square peg, but we need to fill that because now I want a different kind of axle. So this time pull off a cylinder primitive, and it's going to be about 30 by 30, I think, just looking at it, 30 by 30. I will do that 32, so it's all the same height. Center them to each other. And if we merge that, then we'll get a flywheel. But we want to have a center hole in it, and I want this center hole keyed. So this time, pull off yet another cylinder, and I want the axle to be 8 millimeters by 8 millimeters. And this is 30, remember. So let's make that 40 so it pokes out a little bit. It just means that we can grab it later. Center it. And I want to key it. So I'll need a key cutting in that. I need a section of it flattened. And I want that section to be 2 millimeters. Remember, this is 40, so let's make this 45. It means that we can grab it really easily. And now we need to center it to the axle. So we center it there, hit the centering, the alignment key, center it to one edge and to the center there. Now we can turn that into a hole. We can join it with the 8 millimeter bar that we just did. So we group them. And we're going to get a flat keyway. If we click on that and now make that a hole, highlight the whole lot and group them, then we get the flywheel with a flat keyway at 8 millimeters. The other thing that this will be really good for are the two gear sets that we need to make. But at 150 by 150, that's a bit large, so we can re-import it. But you'll notice here we've got a scale. So we can make that half the size by making that scale 50% and import it, and it will import it at half the size. And there it is. Now I want this gear to be about 5 millimeters thick, and it's 75 by 75, of course, because this was 50 by 50. So I need to shave off a bit to make it 5 millimeters thick. So if I move it 5 millimeters from the bed, make that 80 by 80, align the two by highlighting them and hitting the align key. And then group them. We have a pretty little shape that will look nice when it comes to the gearing that we're going to do. Again, we've got this square hole, which won't do. So if we grab a cylinder primitive, smooth that out, that looks about 14 to 14 to me. Yep, pretty cool. And then we can align those to each other. So we center it to that. And make this 5 millimeters high. And we can put an axle straight through by pulling on a hole primitive, smoothing it, 8, 8, and then we can center the whole thing to it, group them. And there we go, we get a nice center. Now, of course, that needs to be geared. So we go to search, type in gear, pull out metric gear. We want that to be 5 high. And you'll notice that this is 19. This is 75. So we need it to be bigger than 75. Let's change the module because I think 1 is really not chunky enough. So 1.5. And so if we change that to something like 50, then we get 77. And that is 75. So we'll have 2 millimeters. It's not quite enough. So let's change it to 52. Now what we want to do is place that in that. That's 75. So let's close this, grab ourselves another hole primitive, smooth the sides, make that 74 by 74. So it's just a little bit smaller than this. That means that will overlap with this later on. And if we've aligned those two, We can check out. We're not cutting into the teeth. No, we're not. So let's group them. Then all we have to do is highlight those two and use your alignment button to align them. And group them. Hey presto, we have our gear. Duplicate that and move it out of the way. And we have two gears and a flywheel created in a few minutes because we basically reused old parts. Now, of course, I need to draw the other parts, and here they are. And I don't plan on going into how to draw these parts because they're all basic primitives, and I have covered that in previous videos. And I will be putting these parts up on the Thingiverse should anybody want to print it off or anybody want to use those parts to redesign for themselves. All I really wanted to point out was it's more than possible to reuse your parts or parts of a design to speed up your drawing process. Okay, let's get them printed out and put together. Right, to put this together we have two gears labelled A and B and two axles, a long one with a flat side and a short one. Into gear B, the short one goes into the reverse side so that it's flush with there and a bit of glue to hold it into place. Then in gear A we take the long axle and shove it in there so the flat side is facing that way and glue it into place. And then we have two counterweights. The counterweights have this large hole with a little notch in it and there's a corresponding notch on the gear. The counterweights go onto the notch and glue into place on both of the gears. Like that. Then we take these pegs with the step in and those pegs go into the counterweights right there. Then we have the base and the back plate. The back plate's got this angled section and you glue the back plate onto the base that way so that the long side of the base is back and the short side is the same as the angled section. When you've done that, take the cog with the large axle and feed it through the back plate. Like that. There's a washer, a thin washer at 1mm, that then goes on. Then we pop on the flywheel to line it up. There we go, and right there we pop on one of these clips. Now we want to put on the cog with the small axle, and what you do is rotate that round so that it's at 90 degrees, making sure that's one at 90 degrees, and then pop the axle through, keeping them at 90 degrees from each other, which is why it mattered that it was A and B, and when we've got those on, they should be in line. And when they're in line, flip it over and pop a clip on. Now we take our crank arms, one straight crank goes there, one straight crank goes there, then you've got these ones with a bend in the crank, that crank goes there, and that crank goes there, and again, at the top there, we pop a clip on. Then we have these connecting shoes. One's got a 6mm hole in it and one's got a much smaller 3mm hole. The 6mm hole goes up against this here and it goes up from underneath. Then there is this arm which snaps on the top. And when we've snapped it down, we pop two clips and repeat that with the 3mm hole on those. Then this, which is a bit of 6mm bar with the hole right the way through, goes through there and into that 6mm section and you glue it in place. And then this, which is a bit of 2.8mm bar, feeds all the way down into that section and again glues in place in here. And when you've done that, this is what you get, the Rhombic Drive. Now if I move the flywheel, what you can see is that these two piston rods move independently of each other and 90 degrees apart as the rhombus right here gets deformed. Of course what we actually want to do is drive the piston rods, which will do the same thing, but we can see it moving as it should move. Now I will put this up on Thingiverse of course and the link will be in the description. There is a variant of this incidentally, where these extend to the crankcase and have a pivot point, and if you do that, you can get rid of one whole half. But this is the original full Rhombic Drive, which, as I say, is used in Stirling engines. I hope you enjoyed the video. I hope it was useful to you. Thank you very much for watching, and please do remember to like and subscribe.